In topological materials, electrons can display behavior that is fundamentally different from that in conventional matter, and the magnitude of many such exotic phenomena is directly proportional to an entity known as the Chern number. New experiments establish for the first time that the theoretically predicted maximum Chern number can be reached, and controlled, in a real material. When the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics 2016 to David Thouless, Duncan Haldane and Michael Kosterlitz, they lauded the trio for having opened the door on an unknown world where matter can assume strange states. Far from being an oddity, the discoveries of topological materials hold the promise, for instance, to lead to novel types of electronic components and superconductors, and they harbor deep connections across areas of physics and mathematics. While new phenomena are discovered routinely, there are fundamental aspects yet to be settled. One of those is just how strong topological phenomena can be in a real material. Addressing that question, an international team of researchers led by postdoctoral researcher Niels Schröter provide now an important benchmark. Writing in Science, they report experiments in which they observed that in the topological semimetal palladium gallium PdGa, one of the most common classifiers of topological phenomena, the Chern number can reach the maximum value that is allowed in any metallic crystal. That this is possible in a real material has never been shown before. Moreover, the team has established ways to control the sign of the Chern number, which might bring new opportunities for exploring, and exploiting, topological phenomena. Developed to the maximum in theoretical works, it had been predicted that in topological semimetals the Chern number cannot exceed a magnitude of 4. As candidate systems displaying phenomena with such maximal Chern numbers, chiral crystals were proposed. These are materials whose lattice structures have a well-defined handedness, in the sense that they cannot be transformed into their mirror image by any combination of rotations and translations. Several candidate structures have been studied. A conclusive experimental observation of a Chern number of plus or minus 4, however, remained elusive. The previous efforts have been hindered by two factors in particular. First, a prerequisite for realizing a maximal Chern number is the presence of spin-orbit coupling, and at least in some of the materials studied so far, that coupling is relatively low, making it difficult to resolve the splittings of interest. Second, preparing clean and flat surfaces of relevant crystals has been highly challenging, and as a consequence spectroscopic signatures tended to be washed out. Schröter et al. Have overcome both of these limitations by working with PdGa crystals. The material displays strong spin-orbit coupling, and well-established methods exist for producing immaculate surfaces. In addition, at the Advanced Resonant Spectroscopies beamline of the Swiss light source at Psi, they had unique capabilities at their disposal for high-resolution ARPES experiments and thus to resolve the predicted telltale spectroscopic patterns. In combination with further measurements at the Diamond Light Source (UK) and with dedicated ab initio calculations, these data revealed hard and fast signatures in the electronic structure of PdGa that left no doubt that the maximal Chern number has been realized. A hand on the Chern number, the team went one step further, beyond the observation of a maximal Chern number. They showed that the chiral nature of the PdGa crystals offers a possibility to control the sign of that number as well. To demonstrate such control, they grew samples that were either left or right-handed, see the figure. When they looked then at the electronic structures of the two enantiomers, they found that the chirality of the crystals is reflected in the chirality of the electronic wave function. Taken together, this means that in chiral semimetals the handedness, which can be determined during crystal growth, can use to control topological phenomena emerging from the behavior of the electrons in the material. Thanks for watching. Do you like my video? Then show me your love by pressing like button. Please subscribe my channel and hit bell icon for new technology updates. Bye bye.